All right, so for today, what we're going to do is we'll take a slight digression into a more mathematical topic on loop invariants, and then we'll sort of come back to go back to sort of discussing the entire process for BFS. So if you recall from the last lecture, we discussed certain properties that BFS had. So let me actually pull up those notes. And so just to recall, we did breadth first search, and we proved, or we stated the following. It's actually a mathematical theorem. We said when BFS terminates, the following hold. Visited V is true if and only if V is connected to S. The predecessor of V is null if and only if V is equal to S, that V is the start vertex, or V is not connected to S. And the third important property is for V connected to S, the vertices V, predecessor of V, the predecessor of V, so on and so forth, form a shortest path to S. So we stated this. But how does one actually prove such a mathematical fact? This is actually a big topic in of itself, and I will not be able to do full justice to it. Today, I will just give you a flavor of how one proves these statements. And more detailed discussions of this are usually in 102. But it's important that if you get a chance to read CLRS and to understand more about loop invariants. So let's start by asking the following question: how to prove that BFS starting at S actually finds.
Yeah, Sesh?
Yes?
I have a question. I tried to ask it in the session, but I was told I should ask this to you directly. How is it possible that I got a 2 on my homework when the autograder said pass?
So you're going to have to come and either talk to me after class or during office hours, and then I can address that.
Because it seems like it's mathematically impossible to me, right? If the autograder says pass, it should be at least a 5, like at least half credit.
There was a certain edge case that got a lot of people's code as far as a large amount of duplicate words, and so you should probably go over it in office hours.
I'm sorry, this is for which homework? Homework 3? Oh, homework 3, just because you pass the test doesn't mean you will get any points. There's no, yeah. Yes, there is. It's still the end of the week. So again, I think all right, so continuing with the lecture. So how to prove that BFS starting from S actually finds shortest paths. And this is actually a fairly challenging statement to prove. And the technique that is used is you have to discover something called a loop invariant. So a loop invariant is a statement. It is a statement parameterized by the, and I will make this clear with an example, but let me just write the definition. Parameterized by the number of iterations of a loop. It's a statement parameterized by the number of iterations of a loop, is typically trivially true at the beginning of the first loop and is proven by induction. Induction over the number of iterations. And finally, the statement after the last, and this is commonly the statement after, well, okay, so let me just sort of ignore that point and I'll come back to it later. So I'm going to start by taking a very simple example of insertion sort, because that's an algorithm that we all know, understand, and love. And let's try to understand how one proves that insertion sort works correctly. And so remember, the input is an array A of length n. And so I'm just going to write this sort of in my mixed pseudocode. So for I going from 0 to n minus 1, let me just sort of open up the braces of the loop. I'll say I set j is equal to I, and then I have a while loop. So I have while j is greater than 0 and a of j minus 1 is greater than a of j. While it happens, swap a of j minus 1 and a of j, j minus minus, and that ends insertion sort. J is equal to I, I'm sorry. How does one prove that insertion sort sorts correctly? And you sort of have an intuitive view of why that is the case. Let us now try to mathematically prove that insertion sort is correct. So we need to discover the loop invariant. And so let me write down a statement, which is the loop invariant. And the statement, the loop invariant. And by the way, the loop invariant is by no means unique. There are many possible loop invariants. And what I'm describing is a single loop invariant, is one loop invariant. So I'll say for all 0 from I to, for all I going from 0 to n minus 1, after I iterations, so after I iterations of the outer loop, the array A going from 0 up to I is in sorted order. Right? And this is not a surprising statement. You intuitively understand this to be the case, that when insertion sort works, after I iterations, insertion sort has processed the first I elements and has put them in sorted order. This is a loop invariant, and this is a statement that we can mathematically prove, and we prove it through induction. We prove it through induction, and the proof is going to be like, it's like you write down a proof, and the proof will be descriptive. It's in English. It doesn't mean it's not math. It is a formal proof written down, just in the way that you do proofs in CE16 in discrete math. This is a proof by induction. Now let's just understand the loop invariant a bit before we dig into actually how we would prove such a statement. So the loop invariant, so at I is equal to 0, the loop invariant is simply saying that A0 is in sorted order. This is trivially true. And this is the base case of the induction. Right? So this is the base case. So now we have to do the induction. And so note that if you set I to be n minus 1, that means it says after n minus 1 iterations of the outer loop, the entire array is in sorted order. So you see that what the loop invariant does is the last statement in this set of statements, the last statement is actually a proof that insertion sort is correct. So what would the induction say? It would say, well, assume, and we can do, strong induction here, but normal induction is enough. So assume statement is true after I iterations, right? And I is going to be strictly greater than 0. Let us prove a statement after I plus 1 iterations. Okay? So this is the induction hypothesis, right? This is the hypothesis. And let us prove the statement. This is where we're doing the induction. And so what we're saying here is the picture. Up to I, this is all sorted. And now we're looking at the I plus first element, and we need to sort of argue that this is going to end up in sorted order. What I'm going to do now is I'm going to kind of write down the proof, and you can read through it. I want to emphasize just, to be clear, that I'm not going to demand that you reproduce these for an exam or a test. Understanding loop invariance is very important, and this is just a small taste of loop invariance. So I recommend that, you read through this, and if you want to learn more, you go and read CLRS. I believe it's a second or third chapter that talks about loop invariance and how to prove algorithms are correct. Okay, so let us prove the statement after I plus 1 iterations. So in the I plus 1th iteration, J is initialized. J is initialized to I plus 1. Right? So J is going to start over there. And so A of J is A of I plus 1. Of course, because J is initialized to I plus 1. Now observe that throughout the running of the inner loop, Aj is always A of I plus 1. Now, what do I mean there? I mean that what happens is, if you see what happens in the inner loop, it swaps Aj and Aj minus 1 and then it decrements J, which means that A of J is always pointing to that last element. Right? A of J, or I should say J, is always pointing to the last element. J is always the index. J is always the index of this element, which means throughout the running of the loop, Aj is always Ai plus 1. Okay? Now the question is, we need to argue that when the loop finishes, we need to argue that when the inner loop terminates, A of 0 going to I plus 1 is in sorted order. This is what we need to argue or to prove. And so when the inner loop terminates, Aj is J minus 1 is less than or equal to Aj, right? That's this condition here, or J is equal to 0. Or J is equal to 0. So we need to argue that when the loop terminates, we know that these conditions are true. So we need to argue that when these conditions are true, when either of these conditions are true, the resulting situation for A up to I plus 1 elements is in sorted order. Any questions at this point? Like, I've been doing a lot of speaking and writing, so I'll take a pause, a breather, and I'll answer any questions that you have about this. Mm-hmm. Exactly. The subarray which just contains one element is sort of trivially in sorted order, right? Because, right? Yeah. Any other questions?
So, like, I guess in layman's terms, is a loop invariant just saying like certain cases that must be true after every iteration?
It's kind of talking about the evolution of the algorithm. Right? The loop invariant is kind of telling you how is the algorithm evolving. Like, what you want to prove is that actually the final result is sorted. But to get there, you need to argue that all the intermediate steps are doing their job. And that's what the loop invariant is saying, that every intermediate step is doing its job.
Okay, so it's just saying after a particular iteration of the loop, this much of the array should be sorted.
Exactly.
Okay.
But what is interesting about phrasing it in this way is that now you can prove it by induction. Like, you want to write a mathematical proof that insertion sort is correct. Right? You want to write a math.
Hey Sesh, I have a comment I just remembered I meant to tell you earlier. Your note 15 is actually linked to note 16. And the reason I bring it up is the test is today and people might want to look at that note. They can just change the URL by going in and editing the 16 to a 15 and get the note.
Okay, so I'll fix that. Yeah, I'll fix that. But any questions about this? Any questions about what's going on here?
So in general, a loop invariant is just a statement that, or a statement or a pattern that basically holds true with each iteration of a loop.
Exactly. But in some sense, let's say, either the creativity or the insight isn't to come up with a loop invariant that reveals as much about the algorithm as possible. If that makes sense. I mean, you can come up with loop invariants that are not interesting. You could say that after I iterations of the loop, you could always say that A0 is going to be in sorted order, which is always trivially true. So it's easy to come up with trivial loop invariants. Or you could say at the beginning of the ith iteration, J will be set to I, which is trivially true. So it's correct, but it's not really a statement that reveals anything about the algorithm that you're trying to understand. So you should think of a loop invariant as some kind of a statement that is tracking the progress of the algorithm. And as we will talk about loop invariants for BFS, where things are actually much more complicated. But what I want to emphasize here is even an algorithm as simple as insertion sort, which most of you probably intuitively get why it's correct. To formally prove that insertion sort is correct requires some work, and it requires some thought. And that formalization is done through induction. Questions?
Maybe kind of a silly question, but when you define like a loop invariant as, you know, it has a parameterization, so you're looking at, like, in this case, I between 0 and n minus 1. Here we're talking about like a for loop, right? But if you had, say, like a while loop and the condition was a little more complicated, you couldn't parameterize it that easily.
You could still parameterize it by after I runs of the loop. Right? You could still you could still say that, right? Because to do induction, you need some sort of something like I. You need to parameterize by some natural number.
Yeah, that's what I figured, like, to do the base case and the inductive step.
Right.
Yeah.
So maybe you'll do something like you might parameterize it by how much of the input is seen. Or in the case of BFS, how many vertices are visited.
Right.
So you can parameterize by something else, but typically it's sort of like, each running of the loop is like one event. And you're parameterizing by the number of events that have happened, if that makes sense.
Yeah, that makes sense. Thanks.
Yeah. Okay, so, and even writing out the proof of insertion sort, it's a lot of text. It's a fair bit of text, and again, I believe that CLRS has it, so please go and read that up as well. And I might not write everything in full detail simply because I don't have time to write everything out during the lecture. I want to cover things about BFS, but I want you to understand the logic of what is happening. So to come back to this point, we need to argue that when the inner loop terminates, A0 to I plus 1, that's going all the way to the end, is in sorted order. We know that when the loop terminates, Aj minus 1 is less than equal to Aj, or J is equal to 0. Now, something that we can argue, and I'm going to leave this as an exercise. So I'm going to write this as a small claim, and you can easily prove this. And this is a little claim that consider the ith outer loop. Right? So you're looking at the outer loop, the ith outer loop, just as we've been doing here. Or let me use the terminology over here. So I'll just do the I plus 1th outer loop. That's the one we're looking at. At all times, Aj is strictly less than Aj prime for all J prime that are greater than J and less than equal to I plus 1. So what this is saying is that as the swapping happens, so this was your initial sorted part, and then at some point the sorted part is here and J is there. Aj is going to be less than all of these elements. At all times Aj is strictly less than Aj prime for, and you can prove this is an exercise. And it's basically because of the swapping, right? It swaps when this condition holds. When Aj plus 1 is greater than Aj, then it swaps. And it decrements J. So this, I'm going to just write down this claim. And then assuming this claim, with this claim now, the proof will hold. Okay, so now let's just prove this. We'll just say case 1, J is equal to 0. By the above claim, Aj equal to A0 is strictly less than A1, A2, up to Ai plus 1, right? It's less than all the other elements. The order among A1 to Ai plus 1 is not changed by the swaps, because the swap always involves Aj, Right? The swap always involves aj. So the order amongst those are not changed, and therefore a0 to I plus 1 is in sorted order, right? Because a0 is less than all of these elements, the order amongst those elements has not been changed, and that's all by the induction hypothesis. Technically, this is in sorted order. Then let's look at case 2. J is not equal to 0, so for some j that's greater than 0, and I guess it would be less than or equal to I plus 1, aj minus 1 is less than aj, because that's how it terminated, or I guess less than or equal to. All right, so in this case, what has happened? We are in the situation where here's j, and this is I plus 1. Okay, so the swaps do not change a of 0 going up to j minus 1, which by the induction hypothesis is already in sorted order. Right? It's already in sorted order. The swaps do not change the order in a of j plus 1 to I plus 1, which is also already in sorted order, right? And both of this is also again the induction hypothesis. By the claim above, a of j is less than a of j plus 1. Right? We argue that at all times a of j is strictly less than a of j prime for j prime that is greater than j, strictly greater than j. By the case condition, a of j minus 1 is less than or equal to aj. Right? So what's saying is that all of this is sorted, and aj lies between a of j minus 1 and a of j plus 1. Thus, a of 0 to I plus 1 is in sorted order. This completes the proof, and we're done with the induction. So this is, in some amount of gory detail, is the entire proof that insertion sort is correct using a loop invariant. Okay, so this is a bit much. It is challenging to sort of understand all of this the first time you see it. You will have to go back, read it, and maybe reread it a few times. But then it'll make sense. I want you to get the basic picture. I wrote all of this down so that it's available for your notes. And you can go and read it up. I will, scan this and put this up. But are there any questions about the basic logic, the basic idea of the proof, and how we're proving that insertion sort is correct using a loop invariant?
So it's like slightly different from how, like, I think a lot of us have been exposed to induction before, where you have kind of like the, base case for when it's just 1, and then you get k, and then proving that k implies like k plus 1 and stuff like that. So I guess it's just like a little bit confusing. So is the basic format just you have case 1 and then case 2?
No, case 1 and case 2 are not part of the induction. The actual induction is this step. There is a base case and there is an induction. There happens to be a breakup of cases inside the induction. The case 1 and case 2 are within the induction. And the reason there is case 1 and case 2 is really because when the loop terminates, it could terminate because of j greater than 0 or because of the other reasons. So that's why you have case 1 and case 2, depending on which was the cause for the loop to break.
Oh, I see.
Right? That's where you have case 1 and case 2. Yeah.
Okay.
So I think a common point of confusion for a lot of students is they look at this and they say, this is a lot of English. This doesn't look like a proof, or this doesn't look like math. And indeed, what I would like to say is that, no, I want to correct your view. This is math. Indeed, this is the way that one writes proofs. And proofs are arguments. They're sort of logical arguments that end up, are written in a combination of English and math symbols. And induction is the way that you prove that algorithms are correct. Questions?
But to the point of what Tavion was saying about when we learned induction, I learned it pretty much the same way. You prove one step and then the next, and then plus one, etc. I know you just explained that to him, but I didn't really get how you showed that.
How I showed that the induction is proceeding?
Yeah.
So let's go back to this argument. So we started by proving the base case for I equals 0.
Right.
And then we're going to do an induction step where we assume the statement is true after I iterations, and we prove the statement after I plus 1 iterations. That's the induction step. And everything that follows was the induction step.
Okay.
Right? And within whatever followed, so the aim of everything after this line is just to argue this part, which is that the statement is true after I plus 1 iterations. Assuming the statement is true after I iterations. Where do you use that assumption? Well, you use that assumption in saying that everything up to I is sorted. So eventually when j ends up somewhere, it's going to break this up into two parts. But both of those pieces are already sorted. And that's where we're using the induction hypothesis, and that is exactly what is written over here. Which is, you're looking at...
Okay, that helps.
Where you're looking at the order with 0 and j minus 1, you say by induction, that's already sorted. From j plus 1 to I plus 1, that's already sorted, because the swaps are always, the swap is always with the new element. It is never swapping two old elements. It's always swapping a new element.
Okay, that helps a lot. Thank you, Stash.
Yeah. So anyone with their hand up, just go ahead and shout out so that I don't have to.
Is proof by strong induction ever necessary for like algorithms maybe we encounter in 102?
Yes, often strong induction can be used, like when you have a more complicated algorithm, especially ones that, I mean, here it's sort of straightforward in the way that, there's a loop and there's something decrementing, but sometimes you have conditions where things jump from one to the other, where maybe, so strong induction is used. Strong induction can be used. Formally speaking, even like the proof that things about the AVL tree, the fact that the AVL tree actually maintains its balance conditions after all those rotations, all of those proofs are technically should be done by induction. I kind of did them in a more hand-wavy way. I showed you the pictures and I made the argument, but to prove it formally, you would use induction. Again, like, this can take some getting used to. This is not at all obvious, and I recommend that you read it and you reread it. But at this point, if you're missing specific details on what's going on, that's okay. But you need to understand the overall logic of how one proves the loop invariant. Questions? All right. So let's go now and let's talk about BFS and what is the loop invariant of BFS. And this is going to be much more complicated. So the loop invariant of BFS, this is more challenging. To show you the loop invariant, I'm going to start with a simple example. I'm going to take a small graph, and I'm just going to run BFS on the graph. So I'll say the neighbors of S are going to be V1, 4, V2, V3. Sort of drawing out a very specific example so that you can see what's going on. So V1 is connected to V4. And let's say that V1 is connected to U1, U2, U3. V2 is connected to U1, and V2 is connected to W1 and W2. So I'm just drawing a graph here. Here's my S. Now what I'm going to draw is the situation in the queue after sort of every iteration. So first S gets visited. So I'm going to draw the queue. Okay, this is going to be the front of the queue, and this is the back of the queue. Now I'm just going to write out what are the shortest path distances in here so that we see a picture. So the distance of V1, V2, and V3, that's 1. So I'm just putting 1 over here. Those are at distance 1. And these are at distance 2. These are at distance 2. Sorry, this is it's a bit messy the way I wrote it. So V, these are at distance 1 and everything else at distance 2 from S. Okay, so let's start the queue. So what's going to happen first is V1, V2, V3, and V4 are going to enter the queue. And I'm just going to write their distance to S at the top. Okay, so this is the queue. This is what the queue looks like. Okay, now what's going to happen is that we take the front of the queue, we remove it. So V1 is going to exit the queue. So you have V2, V3, V4. These are all distance 1. V1 is going to visit its neighbors. So V1 visits V4, but V4 is visited, so nothing happens. Then V1 is going to go to U1, and then U2 and U3 are all going to get inserted into the queue. So you get U1, U2, U3, and all of these are at distance 2. Okay, now let the queue proceed one more step. V2 is going to get dequeued. So we have V3, V4, U1, U2, U3. So V2 got dequeued. Now V2 has a neighbor U1, but U1 is already in the queue. So then V2 is going to add W1 and W2 to the queue. W1, W2 to the queue. And those are going to be at distance 2. Now V3 is going to get dequeued. Maybe V3's got some connections. So you'll have V4, that's 1, U1, U2, U3, W1, W2. These are all at distance 2. Now this is going to add some stuff to the queue. It's going to add some stuff to the queue. What are the distances of those vertices from S?
Two.
Why 2?
It's 1 more than V3 was from S.
It's 1 more than V3 was from S. So everything that is going to get enqueued here is going to have distance 1 to V3, right? It's a neighbor of V3. It cannot have distance 1, because if it had distance 1, like if you had a neighbor at distance 1, well, that's already been added into the queue. So everything added here is going to have a distance 2. Do you now start seeing what the loop invariant of the queue is? There's a queue invariant. The data structure, the queue is going to have a very specific property. What do you think the property is going to be? And I've sort of written it out over here. Anyone want to hazard a guess?
So it queues. It queues according to the distance.
I'm sorry. Say that again. Say that again.
So it enqueues according to the distance, and as it goes further and further, the distance that was closer gets dequeued. The property.
Right. Okay. So one thing that you can see in the queue is that things that are closer to S appear before things that are further. Okay, that is one property.
Could you basically say something like for all I, where I is the distance from a node to the source, I going from 0 to the maximum distance, at each of those iterations, all the nodes at that distance I would have been visited?
At each of which iterations?
Right,
but no, you're along the right track. So someone else had sort of spoken up in the middle, so...
Okay.
No, go ahead. Someone else had spoken just before, but I forget. Like, do you mind commenting again?
Are you talking about me?
No. Just when you were speaking, somebody else spoke up and then stopped. Sorry. Okay.
I did.
Yes.
But then I wasn't sure. I was wondering, like, can we argue that all the nodes and queues are just basically sorted based on their distance?
So yes, okay, so that is true, that they are sorted based on their distance. And then the next comment was that, there is a distance so that everything up to that distance has been seen. But let me ask you, now here's a specific thing. How many distinct distances do you see in the queue? You see only 2 distinct distances. Can there be vertices of 3 distinct different distances in the queue?
Not until we're done.
Oh, no.
Never. So you can actually never see more than 2 distances in the queue, because you always start by pulling out a 1, so whatever you add is going to have distance 2. It's only when the 1 gets cleared out that you'll ever start seeing distance 3. So the queue only has 2 different distinct distances. Moreover, when the first vertex of distance 2 is seen in the queue, all the vertices at distance 1 have gone through the queue. So we're making these observations about the queue, and this is the loop invariant. And this is what we will write down formally. I'm not going to write a formal proof of this. I would love to, but it would take an extra lecture to cover. And CLRS has details on this. But this is sort of how you discover the loop invariant. You go through the algorithm, you track the main data structure, and you see what's going on and try to discover patterns in it. And once you run it on a small example, you start discovering this pattern.
So sorry, just to quickly ask, like kind of like a general rule of thumb, since you said that like for any algorithm you can think of even trivial loop invariants, but it's important to devise one that actually tells you information about the algorithm. So are you just saying, generally speaking, like if you have an algorithm involving some data structure, the ideal loop invariant is something which describes the behavior of that data structure and like how it changes as the algorithm progresses?
It's, I mean, especially, if you kind of stare at BFS for a while, you realize that BFS, there are only sort of 3 things there, right? There's a queue, there's a visited array, and there's a predecessor array. Right? Those are the only things that are sort of being manipulated.
Right. Okay.
But the output has something to do with shortest path distance.
Yeah.
So you have to relate what is it that you want about the output to what is happening with the data structure.
Okay, got it. Thanks.
Which is, again, is not a trivial thing to do, and especially for BFS, the loop invariant is pretty hard to discover. You have to kind of walk through enough examples to see what's going on. And this takes a fair amount of practice and effort, right, and training. But think of this as a taste of trying to understand. Like, this is how one actually mathematically tries to understand or describe an algorithm, and through this invariant. So an invariant is something that doesn't change. Just like, remember, for AVL trees, we had the AVL invariant. For BSTs, you have the BST property, which is also called the BST invariant, because it's something that does not change. So I'm going to now write down the loop invariant of BFS. So let me first answer any questions that you have about this.
Yeah, does this effectively prove that every path that BFS will give us is in fact the shortest path?
So it will prove it's going to, but this is going to be like a step along the proof. The loop invariant that we're going to state is not going to explicitly say that, but we can derive that from the loop invariant.
Right, gotcha. Thank you.
So I'm going to write down the loop invariant, and then I'm going to argue how you use that to prove that BFS finds shortest paths. Okay, so what is the loop invariant? And I should state again that there are multiple different ways of phrasing this loop invariant. Different books may do it in different ways. And so what I am stating here is probably slightly different from what's there in CLRS. So I'll say after I runs of the while loop in BFS of S, and just to recall, what is that while loop? The while loop that I'm talking about is basically the main loop that says, when the queue is not empty, you dequeue something. And again, one can phrase this in a different way, and there's probably a cleaner way of doing it, but I just want to write it in terms of so many runs of the loop, which you can also think of as, which is the same thing as I vertices dequeued. After I runs of the loop, there exists a distance that I'll call L, such that so the first property that we have is that the queue contains vertices at distance L from S, followed by I'll say potentially 0 vertices at distance L plus 1. All vertices at distance L from S that are not in the queue, have already been dequeued, which means that they have passed through the queue. They've passed through the queue. Right? All the vertices at distance L that are not in the queue have already passed through the queue. And so this is sort of saying that everything that is not in the queue has already been dequeued. Moreover, no vertex at distance strictly greater than L from S has been dequeued. Has been dequeued at any point. Has been dequeued, up to this point. So this is it's a fairly long and complicated loop invariant, but this is the key. What is it saying? It's saying that when you look at the graph, so here's S, and you've got all the stuff. This has been through the queue. All of this is in the queue. And all of this is not visited. And so what the loop invariant is saying is that everything that is not visited is further from the things that are in the queue, and the things that have been through the queue are closer than whatever is in the queue. And this is intuitively what you want, but you have to state your loop invariant very carefully so that you can actually prove it by induction. But this is the main loop invariant. And this is talking about these three properties of the queue. The queue only has two different distances, those at L and potentially those at L plus 1, which may be 0. Like for example, in the beginning, the queue just has a bunch of 1s, which means that there's only one distance. The vertices at distance L from S that are not in the queue have already passed through the queue. Moreover, no vertex at distance more than L, strictly more than L, has ever been dequeued up to this point. So the loop invariant says vertices are being treated in order, but it's sort of saying it step by step. Sorry, someone had a question.
Yeah, just to kind of add to or clarify for the part 2, all vertices with distance less than L, so L minus 1 or lower, are also dequeued, but at that point we don't really care about them?
No, you distance at most L, sorry. I should have said all vertices at distance at most L from S.
But can it also be stated that all vertices at distance less than, I didn't see that.
You cannot do strictly less than L because there are some vertices that have already been dequeued that have distance L. Yeah, it's less than equal to L.
Less than equal.
Yeah. So it's less than equal to L, things at L and L plus 1 that are in the queue, and everything that's strictly greater than L has never been dequeued. Okay, so this is the basic loop invariant. It's challenging to understand. So I'm going to pause for a few minutes, allow you to read through it, and ask me any questions that you have, any clarifications that you need about what the loop invariant is saying. Given the loop invariant, let us now argue that BFSS returns the shortest path tree and returns a shortest path tree. I'm not going to write out a formal proof of this because I don't want you to get caught up in the verbiage. I just want to draw some pictures and give you the basic idea. Okay, so let's consider vertex V. When does V get into the queue? Because that's sort of when all the action happens. So here's V. Now S is, I don't know, somewhere far away. So what happens is there's some neighbor U, and U is being processed. So U got dequeued, and then all the neighbors of U are being placed into the queue. And that's when V gets into the queue. So that means when does V get into the queue? It means that there is a neighbor U that is the head of the queue. Right? So what you have is here is the queue, and this is the head of the queue. This is the front. And so we have U at the front of the queue. And so U got dequeued, and then V is now going to get inserted. Now let's just say, suppose U has distance L. Now V cannot have a distance less than equal to L by the loop invariant. Because we said all vertices at distance at most L from S that are not in the queue have already been dequeued, which would mean that V has already been dequeued. But we said we are looking at the time when V got into the queue at the when V got into the queue, which means that by property 2, V cannot have distance less than equal to L. By the loop invariant. So V must have a distance strictly more than L. But we know that V has distance at most L plus 1 because V has a neighbor at distance L. That means the distance of V is exactly L plus 1, which is precisely what the algorithm reports. And therefore BFS is correct. Okay, so this is sort of the argument. And I'll write down a few more steps. But this is the logic. So you look at the point when V enters the queue. And you say V enters the queue because there is a neighbor that was the head of the queue. Now that head was at distance L, which means everything in the queue is at distance L and L plus 1. So that's exactly the L that we were talking about in the previous statement. And so all vertices of distance at most L have already gone through the queue. So V could not have been one of those vertices. Therefore V has distance at cannot have distance less than equal to L. Therefore V has distance strictly greater than L, and we argue V has distance L plus 1, which is precisely what the algorithm reports. Okay, so I'll write this out over here. So therefore V has distance strictly greater than L. V's neighbor U has distance L, hence V's distance is L plus 1. And BFS of S correctly determines a shortest path. Because the shortest path from V as constructed by BFS is the shortest path from U. It goes to U and then it goes to S, and this is going to be your shortest path. And again, technically there's an induction here that I'm like omitting. But you can see that this is how it correctly determines the shortest path tree. Okay, I'm going to end my discussion of loop invariants at this stage. I'll take any questions that you have about this, but after that, I'm going to go back and just talk about the algorithm BFS. So those of you who have zoned out, like, please wake up and please, come back to the lecture, because what I'm going to talk about next is important, and it's about the coding and sort of the implementation of BFS. First, any questions about this argument? All right. So far we've talked about BFS from a vertex. What is BFS on the graph itself? And this is, sometimes one talks about just running BFS on the entire graph. So let's see what the output is. So BFS on G, this process would simply say it has two, sort of in some sense, two steps. So first, for all V, set visited V to false, predecessor of V to null. And then for all V, if visited of V is false, run, I should say for all S. It's the same, I'm just using a different variable for the first loop and the second loop. So this is BFS run on the entire graph. So what you do is you simply set all the vertices to false. You say everything visited is false, and then you go ahead and you run it one by one. The output now if you think about it, what happens is that all vertices get visited, and the predecessor stores a collection of trees. A collection of trees. And this is called a forest because it's a collection of trees. So the output of predecessor is a forest called the BFS forest. So think of, suppose you have the following graph here. Which has these disconnected parts. Each of these is called a connected component. So when BFS runs, it's going to, let's say, start at this vertex. It's going to eventually just visit all of these vertices. And it's going to output some kind of tree structure over here. Then it's going to visit this. It's going to output this tree. And then maybe it starts here. And it visits, sorry, I didn't draw my BFS tree correctly. But what you get is a forest, which is a collection of trees, where every tree is a connected component. So just to be formal, for a graph G, and I'll just talk about a simple, which is undirected. Simple undirected. V can be partitioned into connected components And so S is a connected component, and it's a partition loop maximal is a connected component if for all uv in S, U is connected to V. Right? This is a connected component, and it is called S is maximal if for all U in S and W in the vertex, if V is if W is connected, no, I should say if U is connected to W, then W is also in S, which is just saying that it's everything. If anything is connected to any vertex in a connected component, maximal connected component, then it's also part of the maximal connected component. Okay, so the output of BFS is a forest where each tree is a connected component. And this is when you run BFS on the graph. This is one of the most common use cases for BFS, is to find the connected components of a graph. The running time of BFS where there are n vertices, m edges, is, so if you think about it, every adjacency list is traversed exactly once when a vertex is dequeued. And that happens only once, and therefore it's O of m plus n. And it's theta of m plus n. So BFS runs in linear time. Right? So BFS, it runs in linear time, it finds shortest paths, it finds connected components. So it's an incredible algorithm. And there are so many things that BFS achieves.
When you run BFS on a whole graph, are you still getting a shortest path, or is that just to the, like, you don't really know which nodes are your roots, right?
Yeah, exactly. It only gives you shortest path from the root. So you get some information. You don't get all shortest path information. Indeed, and that is a very challenging problem, like to get shortest path from all nodes. You could run BFS from every node, but then you end up with quadratic time. But again, I should maybe clarify, BFS from S is used to get shortest paths. BFS on G is used to get connected components. And this is where, when I was talking about BFS is really a technique to solve many problems. This is where, you use the same method, the same basic algorithm to give you shortest paths. That's in BFS of S. You can use it to get connected components. That's BFS running on G. All right. Any questions?
There are some raised hands.
Yes. Yeah. Go ahead.
Daniel?
I didn't put it down again.
Robert?
Hello.
Yeah.
I was just curious if you could explain connected components again.
Sure. Yes. Yes.
Is S a node or?
No, I'm sorry. S is a set.
Oh, okay.
S is my apologies. I wrote this too quickly. So S, a subset, is a connected component if all the vertices are connected to each other. It's maximal if in some sense it's the largest possible connected component, that contains the set. So if you look at this graph, any subset of these vertices is a connected component. A maximal connected component is everything.
Thank you.
So given a graph, you may want to sort of decompose it into these parts, and these are the connected components.
So in the homework 4, do we need to care about the disconnected and the connected components?
In homework 4, you are not going to have to actually compute the connected components explicitly because you're only finding shortest paths.
Okay, so there's no kind of like graph, they have like 3 separate parts, right?
I mean, I don't know if it has different connected components. I'm not sure about that. I don't remember off the top of my head whether the graph was actually connected or not. But regardless, I don't think it is going to affect. You don't need to find connected components. You need to find shortest paths. So you're going to be running BFS from various source vertices.
Oh, so there's no situation that like one is in the this part of the graph and one is in another part of the graph, and this is to the...
That might happen. That might happen.
Okay.
And I believe that in the output I've said something about that.
Oh, really?
I don't know.
I think that's the no solution, right?
Yeah, then there's no solution.
Oh, there's no solution? Okay.
Yeah, then there's no path. So that is possible. So that's a good point. So the thing is, when two vertices are in different connected components, there's actually no path between them. But BFS can discover that, right? Because BFS will discover that. BFS explores everything and says, hey, I have not touched that vertex, and therefore it's in a separate component.
Okay.
Questions? Any other questions?
Yeah, I had a question about the BFS on the graph. So, from like a coding standpoint, like, what will it return? Will it return like a root node from each connected component? Like, I'm finding it difficult to picture it.
So, what it really returns is the predecessor array. And some of those predecessors are going to be null. Those are the roots.
Okay, thank you.
Right, so that's a good question. So what it's going to return is the predecessor array, right? Because the predecessor stores the collection of trees, and I guess the roots are vertices where the predecessor is null. Right? Those are the roots of the vertices. Those are the roots of those trees. So BFS run on the graph, I mean, it gives you shortest paths from these arbitrary roots. So it isn't particularly useful if you're looking for specific shortest paths. And that's why you would run BFS on G to get the connected components. You would run BFS starting from a specific source to get the shortest paths.
For a simple graph, is a component and a strongly connected component effectively the same?
They're the same thing, right? So in general, when you have directed graphs, you have the notion of strongly connected components, in which case then BFS will not work. And then the algorithm is more complex. You have to use like variance of depth first search. Okay, so any questions about this?
Sashi, I was wondering, if we run BFS on the whole graph, the output is one predecessor array or separate ones.
It's really just
depending on how many connected components we have.
It's really just one predecessor array, and the number of nodes that have a null predecessor is the number of connected components. The number of roots is the number of connected components.
I see. Got it.
But you don't really break it up into, you don't have to break it up into separate arrays. You can if you want, because then you can go back and traverse it and figure out what all the vertices are.
Yeah, that's what I was wondering.
Yeah, you could, yeah, okay, that's a good point. So technically, this isn't returning the connected components as separate sets. It's really returning this one predecessor array that just has all that information in it.
Okay.
Professor, I'm still not sure I get entirely what BFS G is doing. Is it running BFS S on every node within the graph?
No, okay, so what it does is, maybe, let me draw a picture because I think there's some confusion on this. So let's just say your graph has 3 connected components. Let's say 4 connected components, okay? So initially, it's just going to set every visited vertex to be false, and it's going to set all predecessors to be null. That's just how BFS is initialized. Now it's going to go through every vertex, and if the vertex has not been visited, it's going to run BFS from that vertex. Okay, so what's going to happen? It's going to start with, let's say, this vertex. And it's not been visited, so it's going to run BFS from the vertex. What is the output of BFS? The output of BFS is some tree. Now, all of the vertices in here are now visited, so it's all visited. So when it's doing the loop, if it ever sees a vertex in that component, it's not going to do anything. It's just going to go to the next vertex. Right? So
that makes a lot more sense.
Yeah, I should have probably drawn this picture like 15 minutes ago. If it touches any vertex here, it's not going to visit anything. So it's going to then, at some point, it's going to pick some vertex here. And then it's going to now construct this tree from there. Right? And now this has been visited. And so the predecessor array stores the tree. So implicitly, looking things up in the predecessor array, you can go back and find, you can go and sort of mark the connected components. And then you have this, and now this gets visited. And then at some point in the for loop, it's finally going to get, loop over some vertex here, and then all of this gets visited. So the output are basically all of these trees together. Okay. All right, so in the last 10 minutes, let me just talk about sort of a more advanced topic. So let me give you another application of BFS. So we'll say graph G is bipartite, which is also called two colorable if V can be partitioned into V1 union V2 such that all edges go between V1 and V2. So pictorially, a bipartite graph looks like this. Pictorial bipartite graph looks like that. So the question is, given a graph, determine if G is bipartite, right? Or give an algorithm. So let me give you a bad brute force algorithm. Remember, always think brute force. Brute force algorithm is basically try all partitions. Right? That would be the simplest brute force algorithm. You could just go ahead and try all partitions. Okay. So for all partitions of V to V1 union V2, check if the edges go between V1 and V2. What is the running time of this algorithm? What is the running time of this algorithm? How many partitions are there? How many partitions are there?
Two to the n.
You have 2 to the n partitions. And so the running time of this algorithm is once you do the partition, then you have to go and look up all the edges. So you get theta of m plus n to the power 2 to the n. Exponential time. Like if you basically had a vertex with, if you had a graph with 100 vertices, this is essentially impossible with this algorithm. Or maybe you could, I don't know, 100, 1,000, definitely not. On the other hand, what is remarkable, and this is like a good exercise if you want to understand BFS better, is BFS gives a theta of m plus n algorithm for this problem. Essentially, if you run BFS and you start with a vertex, you put it on one side, you put all the neighbors on the other side, so on and so forth, excuse me, you will actually correctly determine if the graph is bipartite or not. The proof of that is not trivial. It's quite challenging. But BFS gives a theta of m plus n algorithm for this problem. Okay. And now let's say, okay, so far so good. So I'll say G is tripartite, which is also called three-colorable, if, you know, V can be partitioned into V1 union V2 union V3 such that all edges go between different sets of the partition. So pictorially, that means a graph looks like this. And all the edges are going this way. There are no edges that are contained within any set. Again, you have a brute force by brute force. And you can check all tripartitions. And so brute force basically gives you like a 3 to the n, like an O of 3 to the n algorithm, to determine if a graph is tripartite. Now the question is there an algorithm for checking if a graph is tripartite whose running time is significantly better? So you can do better than this. Is, let's say, is O of m plus n to the k, where k is some constant. Like you could ask, can you do something like BFS? With BFS you got m plus n. Maybe you can get m plus n squared, you can get m plus n cubed, so on and so forth. And if you've ever heard of the problem called P versus NP, this is exactly the P versus NP problem. This is an alternate statement to P versus N. This is an equivalent statement to P versus NP, which is there an algorithm for checking if a graph is tripartite whose running time is essentially m plus n to the k? And we believe the answer is no. So we believe no. And the reason we believe no is that we think that P is not equal to NP. But this problem is essentially the P versus NP problem. Now, the reason I wanted to show this to you is you can start with something as simple as BFS, which I just taught, and you can start with a simple problem like doing bipartiteness, and you can come up with a clever algorithm for bipartiteness using BFS. But the moment you go to 3-colorability, all of a sudden you end up with something that is much harder. And why that is the case is a mathematical mystery. And that is the essence of the P versus NP problem, if you've ever heard of it. And so this statement that I've written here is an equivalent statement to P versus NP, or P not being equal to NP. So on that note, I will end, and I'll take any questions that you have at this point.